synchronous reluctance motor. No math in this video. Instead, we're going to have a graphic exploration of the interactions between the rotor and the stator. The red magnetic flux lines shown in this opening clip will be very important to us. Our exploration of the synchronous reluctance motor starts with the magnetic circuit. The first step is to break our magnetic circuit into two parts. We've got a stator and a rotor. There's a pivot here, and this rotor is free to rotate. Next, we add a coil of wire and a constant current source. This will give us a magnetic field that flows through this magnetic circuit. You can see here the lines aren't very straight because the rotor is offset slightly. In fact, that's kind of the whole point of the video, is that the rotor is indeed offset. If we were to focus in and look at the magnetic field, you can see that those flux lines are reaching out and grabbing that rotor. And the rotor will experience a torque which will pull it in line with the stator. When that happens, the magnetic flux lines will be very straight, as opposed to the original rather curvy route that they took. So this begs the question, why does the rotor experience that torque to begin with? We could say the lines just want to be short. That's what they do. A closer analysis would say this is a conservation of energy problem. It obeys the laws of thermodynamics. Objects in the real world are only going to move if they're being acted upon directly or if they're moving to a lower energy states. This ball rolls downhill because it's moving to a lower energy state. Now, all this gets really interesting when we start looking at magnets. Back in grade school, you might have played with very simple bar magnets, and you know that the north and south poles will line up. And that gives you resulting flux lines that look something like this. We said that flux lines want to be short, and we want to have a conservation of energy. So if we rearrange the magnets like this, we've kind of accomplished both things. The flux lines are now much shorter, and from experience we all know that the magnets will naturally rotate into this position. They will physically move to make this happen. We're forced to conclude that this is the lowest energy state for these magnets. And since you brought up the concept of conservation of energy, we have to ask, where did that energy go? Let's see if the answer lies in the term reluctance. After all, this is a synchronous reluctance motor. Here we have the magnetomotive force, we have the reluctance of the core, the reluctance of the gap, and then another device representing the reluctance of the gap. In the circuit we have the magnetic flux flowing, shown here. We can simplify this by saying the reluctance of the core is significantly less than the reluctance of the gap. Reluctance core effectively goes to zero. Recall that flux is defined as the magnetomotive force, represented here with an F, divided by the total reluctance. When our rotor moves, the reluctance in the air gap is reduced. If the reluctance is reduced, then the flux must increase. And when that happens, we can say that more energy has been stored in the magnetic field. The units for flux, or phi, is Webers. And a Weber is a joule per ampere. And a joule, of course, is a measure of energy. All things being equal, if you have more flux lines, you have more energy stored in the system. Some folks will talk about inductance, and they'll say that when the rotor is aligned correctly, the inductance will increase. Again, that's a fancy way of saying that the energy has increased. Look it up. You'll see that the units of the Henry are joules per ampere squared. Energy. Now that we have a better idea why our rotor experiences a torque, let's go back and try to make it rotate continuously. One way to do that is to add another coil and commutate the coils such that they turn on at the right time. So in theory, this would work. We would be able to turn on the north-south magnets, sometime later the east-west, then the north-south, then the east-west. But it's a horrible motor. It's not self-starting. Just imagine the rotor is perfectly oriented with the east and west poles of our stator. Under that condition, there's no way to start this. Activating the east-west coil will do nothing for you, and activating the north-south coil will do nothing as well, because it won't experience a torque. The rotor is stuck. And even if you were to unstick it by randomly moving it one direction or the other, you have no control over which way it's going to turn. it's just as likely to turn clockwise as it is to turn counterclockwise. However, the concept is good, and if we shift back to that three-phase motor we showed in the opening slide, we're in business. What you see here is a 4-pole, 3-phase stator with salient windings. Into the stator, we're going to insert a rotor. For starters, we'll just put in a circular core of magnetic steel, which isn't very exciting, but it will allow us to explore what the magnetic fields are doing. For instance, if you turn on the first coil, the blue ones here, that will establish a north-south, north-south poles. The flux lines take the shortest route through the core. And if we activate the second set of coils, shown in purple, we have the same thing again, where the flux lines are taking the shortest route through the rotor. And finally, we can do the exact same thing again with the third set. Once again, we see this pattern where we have arcs across the rotor. These arcs suggest the construction of a rotor. It took a while to construct, but here is a cross-section of a rotor that just might work for our system. Before we install it inside the stator, let's test it. This telephone looking receiver thing is going to be our test instrument. It's in a good position now because those flux lines will follow the thick path through the rotor. But if we move it to one of the other locations, it's not so good anymore. You see, these magnetic paths are all twisty-turvy. I think you see where this is going. We could say that the first test we did had a low reluctance, while the second one had a very high reluctance. And now we take that rotor we just designed and we put it into the stator of our synchronous reluctance machine. It's a thing of beauty because those magnetic paths from the stator will run through this rotor perfectly, if it's aligned properly. Of course, if it's not aligned perfectly, it will align itself. That's the whole point of having a variable reluctance core. There's one in only one position where this thing wants to be. Just like the simple rotor we showed before, this also wants to align itself with the magnetic core of the stator. Remember, this is a three-phase machine. There will be a constant amplitude rotating magnetic field in the stator. The rotor, due to its low reluctance in one position, again, that's where the thick bands are located, will lock onto that magnetic field of the stator, and they will move in lockstep with each other. So the whole thing will operate very smoothly. Sorry, this video is getting a bit long, but before we end, I wanted to talk about the pros and cons of the synchronous reluctance machine. First, it's a synchronous machine. It will turn at a constant speed. It has a high efficiency, represented here by the letter eta. You've seen this before. This is a power flow diagram. We have power in on the left and power out on the right. And then we have losses along the way. A typical motor might have some I squared R losses in the stator. It's going to have some I squared R losses in the rotor, and it's going to have some friction and windage losses as well. There is no winding on the rotor for this thing, so that goes to 0. And since there's no need to cool off the rotor, you can make the fan smaller, so there's less losses in windage. All this combines to make the motor smaller. In general, you have a very simple and rugged machine. On the other side of this table, we have two problems. One is the starting problem, and the other is the overload problem. Actually, in fairness, I'm not sure these are problems anymore, because both are solved with modern electronics. Almost every synchronous reluctance motor is going to include a variable frequency drive, where we take the incoming AC, convert it to DC, and then we have a frequency inverter to take the DC and convert it back to the AC. The whole thing is enabled with a little bit of feedback. That allows the inverter in the variable frequency drive to provide whatever signal is necessary to operate the motor.